Hi, Peter.
Hello.
Well, it doesn't say recording either.
No, I'm just about to start that. Okay.
Hi, Peter.
Okay, ladies and gentlemen, welcome to this week's monsoon seminar. And as you know, our speaker this week is Anne Holbourn. Anne is a research scientist at the University of Kiel in Germany. And as you probably know, she's an expert in micropaleontology and paleoceanography. And I learned this morning that Anne did her bachelor's degree at the Open University in Milton Keynes in the UK and PhD at University College London. She's done a lot of marine research. She's been on 5 IODP expeditions, one of which she served on as co-chief. And she's been on several research cruises on other vessels, including the Marianne Dufresne and the Sonna. So today she's going to be talking to us about Australasian Monsoon. We're going to follow the usual rules where you can, please, if you can mute yourselves during the talk and maybe turn off your videos. And then at the end, I'll call on people to ask their questions. So if you put your questions into the chat, then at the end, I can call on you in order to ask your questions to Anne. And if you like, I will read your question for you, but it might be nicer if you just read it out yourself. So without further ado, Anne, would you like to share your screen and we can start to hear your presentation?
Yeah, sure. So share screen. So can you see it?
Yes, it's good. Thank you.
Good. So thank you, Peter. So good morning, good evening, good afternoon, wherever you are. It's a great pleasure to be here today. And first, I certainly want to thank the organizers for putting together what I've seen as an amazing set of multidisciplinary talks on the monsoon. I very much have enjoyed them. And I think I've learned a lot as well through that time. So today, I'd like to present you some new work that I have done in collaboration with Wolfgang Kund, Steve Clements, and David Hessler. And I also want to show you some of some work of 2 PhD students from Kiel University, Jannika Young and Julia Lubers. So as we all know, the dynamics of the monsoon over Asia and Australia are very much linked to the seasonal swing of the ITCZ, which drives the reversal of winds into both the northern and the southern hemisphere. And this gives rise to some quite distinct subsystems that are defined by their own seasonality of rainfall and wind. The boundaries that I've put here today are quite arbitrary between the different regions, and some people like to subdivide that even more. But really what I would like to emphasize today is the interconnectivity of the regions. And also, I hope by looking at quite a long time scales from the middle to the late Miocene, I hope that it's possible to recognize some of the main drivers of monsoon evolution through that time. So I will be presenting data from 4 sites. 3 were relatively recently drilled, and 1 is a site drilled during the ODP in the South China Sea. This is almost an iconic site now because many people have worked on this site. I know some of you were on the original cruise. Peter was, Wolfgang was, Steve Clements was, and I still think it's an exciting site to work on, and it has taught us a lot about the monsoon. So I will start with this site. And over the years, Steve and Wolfgang and I, we've put together a continuous Bentic isotope record that span the interval from about 18 to 5 million years. And this is what I think is a very exciting interval of Earth's climate evolution. It was a warmer period than the present period. But as you can see here, indicated by those arrows, it was also marked by a stepwise glacial expansion and global cooling. And I think what is particularly exciting, if you look at the main phase of climate evolution during this interval of time, you can see that those steps also coincide with some either quite abrupt or longer progressive transition into those phases. So it starts with the climatic optimum, which is the warmest period of the Neogene, goes through the middle Miocene climatic transition, and then into this still extremely mysterious interval that people refer to as the carbonate crash, when the whole ocean became very impoverished in carbonate. And it has been very difficult to recover complete succession from that time interval, simply because the carbonate accumulation rates are low. There are some areas, there are big hiatuses. So I think this interval, which has been very nicely recovered there, is very exciting to look at. After that, there is another cooling trend, and then we move into the biogenic bloom. And this interval was marked by a major increase in carbonate sedimentation and in productivity throughout the major oceans. Looking at this curve, I think you get a sense already that there is quite a lot of orbital variability in those records. I know they are tuned, but if I showed you the records against steps, I think you would still, it's not very, the records are not very different because the sedimentation rates are not changing in a major way through the records, and you would still identify this cyclicity. But what is striking, if you compare that with an orbital solution, you can very much see that the astronomical metronome is quite consistent, but the delta 18O curve shows those major transitions. So therefore, there is something else at play. And beside the external forcing from insolation, there are also important climate feedbacks that play an enormous role. And those are linked to changes in ice volume, orography, circulation, greenhouse gases, latitudinal temperature gradient. So, and those feedbacks are not just affecting climate in general, but of course they're also very important for the monsoon. So the proxies that we are using in this work, beside the Bentic isotopes, we are also using isotopes of a mixed layer species that lives quite high up in the water column. And we are in the tropical regions where the monsoon is present. The delta 18O, which is captured by planktic forams in close to the surface, is actually providing us a lot of information on precipitation because the signal is strongly imprinted by evaporation precipitation. And although we can, of course, reconstruct the temperature from the same forams and deduct that to reconstruct the local delta 18O seawater, when you have very long record, this is not always possible, but it's very good that just the planktic delta 18O signal itself is very informative. The other proxy that we are using here is the ratio of hematite-goethite. Those are two oxide precipitates that form under very different conditions. One is more diagnostic for dry condition and the other for wet. So the ratio of hematite to goethite is a very useful proxy for continental aridity. And we derive those records from shipboard reflectance spectroscopy data. And those are the new record, the continuous Planktick Delta 18 record that we now have from 1146. We've published some of the earlier record in the lower part, the subquadratus record. This is an ancestral form of rhubarb, which is not present after that time interval. And you may notice that there's quite a high variability in that time interval because this species likely lived slightly further up in the water column and may record a higher variability than the Trilobatus sacculifer species. But already you can see that this record of Delta 18 Planktick shows some definite trend. And I think those trends become very interesting when you are looking at them with the background of the main climate phases. So that you see, for instance, during the climatic transition, you see a stepwise drying. And during the carbonate crash, the values are the highest, and this seemed to be, according to the Planktick Delta 18, quite a dry interval. And then you have a decrease in value and intensification of the monsoon. And then late in the Miocene, after 7 million years, conditions became drier again. So now I want to integrate this with the goethite hematite record of the same site. And we were very happy to see that there is some agreement between those records. And I'll start with the MCO. Those are the lowest hematite goethite value. And this tells us that conditions were likely humid. Also, the Planktick Delta 18, the mean values are quite low. So our interpretation of those trends is that in this very warm interval, we are dealing more with a warm, equable, wet climate, perhaps because of tropical expansion at that time. And during the climatic transition, there is the intensification of a monsoonal climate. It seemed that the climate became more seasonal, and there was also stepwise drying. And the carbonate crash is the driest interval of the whole of the middle to late Miocene. And after 11 million years, we start seeing sorry, I'm going to try and get the pointer. Yeah. So after 11 million years, we see a decrease in the aridity. This is also shown here in a Delta 18O. And our interpretation is that there is an intensification of the summer monsoon, which continues during the biogenic bloom. And you can notice, I think that's also quite interesting, that there is this slight increasing trend here in the Planktick, which matches the Bentic trend. So it seems that the climate also became cooler. And I will talk about the last interval in the later stage of this presentation. So now I want to have a closer look at this interval of the carbonate crash and transition into the biogenic bloom. And I think it's very nice to look at, for instance, the Bentic Delta 18 and Planktick Delta 18 in the early part here, where the amplitude variability is quite low. It seems that there was quite a stable Antarctic ice sheet, and at the same time, very, very low precipitation. And then this picks up a bit after 11.5. There seemed to be a higher sensitivity to orbital forcing during that time. And I want also to draw your attention to those layers here marked at pyrite-rich layers. Those layers are, they appear very prominent here in this hematite-goethite record because they're really a complete change in color from a normally reddish sediment to a gray sediment. I will show you pictures soon. And those layers shows that obviously with this change in color, you cannot interpret the color record anymore in terms of the monsoon, but it does show that there were major changes in bottom water oxygenation. And interestingly, they seem somehow to coincide with quite a change in the rhythm of the Bentic Delta 18O. And there's this very prominent thermal maximum here, which occurs at a time when the orbital forcing is at its maximum. It's a maximum in 100K, in 400K, and also in a long-term modulation of eccentricity. So it's almost reminiscent of some of the warmer intervals during the Paleogene, but of course much smaller scale. But it's a big change from the earlier interval. What I think is also very interesting is as the monsoon intensifies and we are moving into the biogenic bloom, you can see here a very dominant obliquity rhythm in the Bentic Delta 18O. So now I just want to show you one of those pyrite-rich layers, the one that coincides with the thermal maximum. So this is a bit confusing, but the top is here at the bottom, and this is only the upper part of the three sections, 1, 2, 3. But you can see here, this is the top of this pyrite-rich interval. And you can see that about 70 centimeters below, we have a distinct pyrite deposition and calcite layer. And that also affects the Planktick isotope signal. This is in hole A, and you can match that in hole C as well, although we are not really sure when this starts, because if you look at the depths of the layer in the two holes, they are not exactly at the same depth. So there seem to be a lot of changes into the sediment column that occur post-depositional. So now going back to the full record, and I now want to draw your attention to the Planktick Deltas and the Bentic Delta 13C. At the top here, I'm showing you the gradient between Planktick and Bentic Delta 13C. The gradient between those two types of record has been used to evaluate the sequestration efficiency of the biological pump. So that's why I've put those arrows here indicating productivity decreasing during the carbonate crash. So this tells us as well that the carbonate crash is not just due to dissolution of carbonate, but there's also less production of carbonate at that time. And then through the biogenic bloom, we see this increase in the gradient. So it's quite an interesting way as well at getting some understanding of the evolution of both the climate and the ocean at that time. So to summarize this first part of the talk, at our new results from 1146 support an equable warm, humid climate during the climatic optimum, intensification of the monsoon linked to stepwise cooling during the climatic transition. And we suggest that the decreased riverine alkalinity input to the ocean linked to failure of the monsoon contributed to the carbonate crash. And during the biogenic bloom, there appeared to be a positive feedback between monsoon intensification, productivity, carbon burial, and climate cooling. So now I want to move to the Indian Ocean. I want again to look at this interval of the carbonate crash. The site that we look at first is a site which is on the 90 East Ridge. As we all know, the Bay of Bengal is the site of massive terrigenous accumulation from those enormous deltas that are transporting sediments and from the higher ranges in the hinterland. And this site is much more distal, so it's not so directly exposed to the monsoon. And this is work done by a PhD student, Julia Lubers, and this is the interval that covers the carbonate crash and the beginning of the recovery phase into the biogenic bloom. And you may recognize already the thermal maximum. We were very happy to find it because having seen it only at 1146, we always had the thought at the back of our mind that this might be some artifacts and may not be a real global features, but it was amazing when we saw it also in the Indian Ocean. And what this really shows us is that in the Indian Ocean, this carbonate crash starts around 13, and there's a major change again at about 11 million years when we see a slight increase in the carbonate accumulation rates. And this is also shown in this Xrf derived carbonate content. We start the recovery phase. And I think what's quite amazing, if you look at the color of the sediment, we have beforehand this very oxygenated deep water typical sediment. And then we move into a more brownish and into grayish sediment. And this is reflecting both an increase in productivity, but also the advection of clays at that site. So Julia interpreted this as being somehow a signal of the onset of the monsoon, whereas prior to that, during the peak of the carbonate crash, again, we have some evidence for drying in that area. So quickly getting back now to 1146 to look at the very latest part of the Miocene. And this is published stuff, so I'm only going to go through that quite fast. What we noticed over the interval 9 to 5, we noticed that there was a big change in the Planktick Delta 18O. First, the amplitude variability increases, and the mean also is increasing. And if you look at that in the context of the Delta 13C, it's just occurring at the end of this long-term Delta 13C shift. And this is huge. This is a shift of 1 per mil. And this is perhaps one of the biggest shift in the Delta 13C after the end of the Miocene climatic optimum. And it's quite striking that this change in the monsoon occurs at that time. And if you look at the Bentic Delta 18, you can also see this gradual increase and also those dramatic events here, the TG events, which are global events and which we relate to ephemeral Northern Hemisphere glaciation, perhaps at that time. We also at that site have a magnesium-calcium derived mixed layer temperature record. And that also shows that at 7 million years, there's global cooling. And this is also in agreement with the record that have been done by other group, Tim Herbert group, that show very nicely that this is a global signal. And then we have an increase in the temperature, two-step increase in the temperature after those very prominent TG events. And if you look at the delta 13C between Planktick and Bentic, we again see that this interval, when we suggested the winter monsoon intensified, we see that this interval also coincides with the peak of the biogenic bloom. So we were very curious to see how those trends, whether those trends could also be picked up in the Indian Ocean. And we were interested in the evolution of the Indian monsoon in comparison to the Asian monsoon. So we are now going to look at site U1448, which is just at the edge of the Andaman Sea, and it's a much more proximal site. So it's capturing a lot more the signal from the monsoon. And this is work that Jannica Young has been doing for her PhD. And you can see down the Bentic Delta 18O. Now you can, some of those TG events, you can easily identify it also in this record. And what I think is very remarkable is the amplitude variability of the Saculifer Delta 18O, of the Planktick species. This is very different from the 1146 in terms of amplitude. We're really in the heart of the Indian monsoon, and this system is just so powerful. So what we see, one of the first things I think that was quite striking is that all TG events seem to be associated with failure of the monsoon. I'm showing you here the two most prominent events, but if you follow some of the other one, you can see that they occur at maxima in the Delta 18O. Also interesting, there's a change in the amplitude of the variability and the type of cyclicity. So this is even better seen when we are looking at this time series analysis and the spectral analysis of those two different time slices. In the older interval, the precession signal and one of the heterodyne of the orbital signal remain highly prominent. Where when we are moving into the younger intervals, we still have the precession, but we have a more prominent 41K obliquity signal, as well as some other heterodynes. Jannica also generated a magnesium-calcium derived temperature record. And this record was quite striking because it just shows this massive warming after those prominent TG12, TG14 events. And this, again, a two-step warming. And if we compare this to Delta 18O seawater. This has been corrected for ice volume, this curve here, and then corrected again for temperature in the upper curve. There is a massive change. The temperature signal is making a huge imprint on the Delta 18O seawater. And this was interpreting as a change in the moisture origin, a shift to a more southerly moist origin of the moisture for the monsoon during that time interval of warming. Now, I'd like to show you a comparison between the Indian Ocean record and the South China Sea record for that time interval. This is a highly dynamic time interval with this very abrupt TG event and then this warming trend. And we were very curious to see how this would compare. So in the lower panel, those are the temperatures. And this is less prominent at 1146, but you can see that there's again the two-step warming in the South China Sea. And when we compare the Planktick Delta 18O at both sides, the gray curve is the 1146. We again see some change in the cyclicity of this record. It's not as dramatic as the Indian Ocean record, but there seem to be some agreement. So it seems that the changes between the Indian monsoon and the East Asian summer monsoon seem to occur in tandem. And if you superimpose on that the different phases of the Messinian salinity crisis, which to some extent is reflecting the African monsoon, it's quite astounding that there is some very nice agreement between those discrete phases, and also so that, for instance, the driest phase of the Messinian event is coinciding with the TG12 and the TG14. And then after that, we are getting into the phase of we are at the end of the Messinian event. This coincides with this huge warming event. So just a point that I think can be made here is that there seem to be, in this three northern hemisphere system, there seem to be some synchronization of some of those major changes. And I think it's something we certainly have to think more about, but I think it was for us pretty exciting to see that. So now I'm coming to the last part of my talk, and this is work still in progress. And we now want to look at the southern hemisphere component of this huge monsoon system. And during expedition 363, we were able to drill just off the margin of Australia a very, very nice sequence of hemipelagic sediment. And we've been working on this in the last couple of years to try to get very detailed record. And we are at the moment trying to work on the Planktick temperature and isotope reconstruction to complement Xrf and Bentic Isotope data. So the site is in a very interesting position because it's, I don't know whether this is very clear, but this is really offshore the main monsoonal area in northern Australia. And there are sort of here, you can see some of the channels of some of those major rivers that are coming out of this area. this site is certainly in an ideal position to monitor monsoon variability. It's just at the point where some of those big cyclones are coming onto where those big cyclones are coming to northwestern Australia, and it's very much in the track of those big cyclones, which is the main expression of the summer monsoon in Australia. So those are some of those rivers. Those photos were taken post-monsoon, just at the end of actually the monsoon season in May. And you can see that the regime is very, very seasonal. In fact, during the monsoon season, this is covered in water. And this had been the year we went there in 2017, had been a very heavy monsoon, and some of the roads were still not, you couldn't go across some of those roads. So the record that we have generated so far, we've got a Bentic Isotopes, and this is covering the interval 4.2 to, we'll go a little bit further in time to about 9. And you can recognize some of those features already seen in the other records. And also you can identify the Delta 13C shift in those records as well. We have another proxy here to look at the monsoon. We've been able to do Xrf on those cores, and we are looking specifically at the ratio of terrigenous elements, as well as grain size, variability in the core. And I can show you here, this is a picture of part of the core. You can see this really beautiful cyclicity, those dark light cycles in the sediment. And you can also see that the Xrf record picks up the cyclicity very nicely. And this is a precession cycle. So this is a record that we have so far, Bentic Delta 18O at the bottom, and Xrf record at the top. And what surprised us was that we have a major change in the monsoon, in the rhythm of this Xrf data, and this is also happening at about 7 million years. If we look again at the Delta 13C signal, we can see that the change coincides. It's at the same spot as the change that we've seen in the South China Sea. So this seems to be that this change in the monsoon in both hemispheres seems to be very much a synchronous event. And I think this really shows you the importance of this event. Now, we have here a wavelet analysis of the Xrf data, and our preliminary interpretation is that we are moving from a warmer, equable climate prior to about 7.8 million years. And then we see the sedimentation rates decreasing quite a bit in the core, which we interpret as being an aridification of the climate at that time. And then after the cooling event, we move into a real monsoonal regime forced by local insolation. Interestingly, we do not see much happening at around 5.5 million years, as we have seen both for the Indian monsoon and for the Asian monsoon. So this maybe indicate that this is very much a northern hemisphere features, and the southern hemisphere seem for that time to have a different response. But those are very, very preliminary interpretations. As I said, we are now generating the surface records, and I think then we'll be in a better position to understand the full evolution of the monsoon during that time. So take-home message, briefly, I think that what those records shows is that the evolution of the monsoon from the middle to late Miocene was highly dynamic and involved multiple feedbacks. And the long-term developments seem to have been closely linked to variation in ice volume, variation in a latitudinal thermal gradient, evaporation precipitation budget, and the strength of the tropical convection. Major reorganization occur on supraregional scales, and we're certainly not ignoring that this could be linked to tectonic changes and climatic thresholds that are driving the climate towards tipping points. I think what we need now is to integrate much better the terrestrial and the marine records, so we really understand the relationship between tectonic and monsoon variability in those areas. Thank you.
Thank you very much, Anne. We do have a question here from Boris. Boris, would you like to ask your question?
Yeah, it's something in between a comment and a question, I think. Thank you very much. First of all, it was very interesting, and these high resolution data are very useful. I was just wondering if this shift that we see in the dominant cycle that occurs at around 5.6 million years and its obliquity is taking over, if I understood correctly, if this might be linked to the long-term cycle of obliquity that increases in amplitude, I think, at that time, so the 1.2 million year. And if this would mean that the increased effect of high latitude climate might have some impact on the tropical latitude records, overprinting the precession effect.
Yeah, that's an interesting question. I think that in that case, I could be wrong, but I think that we don't directly get the influence of obliquity onto the signal, because if we look at the Bentic Delta 18O, we also don't see that so imprinted into that. So it certainly can have some effect, but we are more thinking that it's the change in the thermal gradient would have favored the transport of moisture from higher latitude, and for that reason, this would be much more visible as an obliquity signal. Whereas if you have the moisture source closer to the, more into the low latitude, then you have much more the precessional insolation signal into it. But it's something that will be interesting to look at once we are looking at our Australian record as well. When you have only one record, it gets quite difficult to really make statements that are absolutely standing in time.
Nice. Thank you very much.
Thank you. And I had a little question. So in the Australian record, it looked like the runoff was increasing after about, what, 7.5 to into the late Miocene, which is, I guess, like a wettening trend, which seems different. Yeah, that thing, exactly. That this trend to wetter conditions seems different from what we see in Asia. And I wanted to make sure I understood that correctly. And I wondered if, is that related to sort of an anti-phasing of the monsoons, or do you think possibly that the northward motion of Australia may have had an effect on the climate in that particular area? Or I just wondered if Australia might be moving north into a wetter climatic belt over that time period.
So you're talking about this interval here from about.
No, I mean after 7. Then this brown on the. It seems like it's getting wetter.
Yes, yeah.
With the runoff, whereas like in most of the Asian records I see, I feel like it gets drier over that interval.
Yes, well, we have also to take into account the sedimentation rates as well. I don't have this here to look at, but we have also to be aware that this time interval, we have a big change in the sedimentation rates that affect the records as well. I think this part is an interesting transition. It's still part of the transitions. And if you look at the South China Sea record, you can also see that the signal, or the Planktick signal, I think I'm going to try and get it from, yes. I think you can see that this is this interval that is not really fully into the winter monsoon as well. So I think that they are, here you would also get the feeling that you have a slight increase, again, a sort of slight reversal into the monsoon, which I think if you look back at the Australian, almost agree with that. So again, we need to look at those records in much more detail than we have done so far.
Was this lower sedimentation after 7 million? Slower?
I think that the sedimentation rates, the lower sedimentation rates are really in that time interval. Okay. And then there is some increase, and I need to check this time interval again. After that, the sedimentation rates are very steady, as you can see, because you see the cyclicity. And I think this trend here at the end is also very interesting when you seem to have a big increase into the monsoon after, but this is not the time interval we've looked at in the other records.
Okay. So we have another question from Christina Lopez. Christina. Christina, you need to unmute yourself. I can do it. At least I think I can do it.
There you go. Can you hear me?
Yes.
Wonderful. Hi, Anne. This is Chris. How are you doing? I love your presentation. So I have one question, is about your runoff proxy. It's the log of calcium over terrestrial input or something? Yeah. Is that correct?
Yeah, over all the terrigenous elements.
Okay. So did you look at the freshwater diatoms?
I'm sorry, I didn't catch your question.
So did you, by any chance, have anybody looking at the freshwater diatoms for this record?
I don't think anyone is looking at that. No, I don't know anyone looking at that.
Okay, because that can help you, as you know, looking at that input from the precipitation and therefore the monsoon. So I'm sorry I didn't hear your presentation from the beginning. So I was just wondering if by any chance you were.
That's a good point. But as far as I know, no one is looking. We have done some work in a more recent interval on cores that have been taken and cover the last few glacial cycles. So this is not going so far in time. And it's been interesting. We've been comparing, we haven't looked at diatoms, unfortunately, but we've been comparing the signal of the Delta 18O seawater in that area, Planktick Delta 18O, with the terrigenous signal. And we find because the ITF, the through flow, the Indonesian through flow, is such a strong feature in that area, we find that the Delta 18O seawater is not actually so representative of the monsoon as the terrigenous input at that site. So I'm not, but I think it certainly would be very interesting to see whether we could get a signal from that.
From at least from the freshwater diatoms.
Yes, yeah.
Okay, and that was from what I saw, an excellent presentation, and I'm very thankful for your work, and I hope to talk to you soon.
Thank you. Nice to talk to you, Christina.
Great. Bye.
Bye-bye.
And I was curious, these Australian cores, are they mostly carbonate?
No, are you talking about the young intervals, or are you talking about the Miocene cores?
The Miocene.
Oh, the Miocene cores are hemipelagic. The carbonate content is about 70–80%.
Oh, okay, still, but there's a significant detrital fraction in there.
Absolutely, yes. And you can see it from that picture that I was showing, that you see this
oh, yeah, right.
That, so they are not really pure carbonate as such. They're very much...
yeah, that looks very interesting, especially for people like me who are less excited about carbonate, or at least don't work with carbonate very much. Leave that to the experts. Does anyone else want to ask a question? Going once, going twice. So if that's the case, I'm going to ask you all to show your appreciation to Anne for her presentation, either by starting your video and clapping, or you can use your reaction button, or both. Thank you. So before you all go away, a couple of business points. If you don't get an email from me telling you when and how to link to the talk every week, then send me an email at my email, which is not very difficult to find. It's on the Monsoon Seminar website, and I'm just typing it into the chat here. And I will add you to the email distribution list. And secondly, come back next week, where Tara Janelle will be hosting this from Queensland, Australia, again, for the benefit of our Eastern Hemisphere friends, so they don't have to stay up into the middle of the night. And check the time. I know it's been moving recently. It's because of all the time changes. That's obviously beyond my control. It'll now be fairly stable, at least over the summer, and at least until the end of our scheduled session up until the summer break. So until okay, so then if there's no other questions, then
Eu não resisto de perguntar aqui umas coisas à senhora.
Thank you very much, and I'll see you all again.
Não quero. Nada.